There is actually a video on the internet that shows you exactly how to get an infinite supply of chocolate. Pretty cool, right? Well, obviously this isn't real. If you take a closer look, the bar actually gets a little bit smaller with each small square you take. But can you actually create something out of nothing? Matter out of emptiness? Yes. Today I'm going to talk to you guys about the theory of relativity, the uncertainty principle, two major concepts in the world of physics. And afterward, we're going to figure out how they fit together to create something from empty space, which I'll explain later. Let's start off with Einstein's theory of relativity. Now, let's begin by imagining a single particle being reflected back and forth two mirrors in a box. And the distance between the two mirrors is going to be dubbed d. So, in other words, d is the distance our beam of light has to travel in order to reach the other mirror. The time needed to cover d is going to be named t. And for demonstration purposes, let's give t the value of 1 second. When this box is not in motion or at rest, our beam of light covers d in 1 second. Let's keep in mind that speed is defined as distance per unit of time. So speed equals d divided by t. Now let's imagine the same box with the same beam of light traveling through space on a UFO. However, our particle now has a greater distance to travel since it has to cover the distance of the box and the distance the UFO has traveled at any given instant. This causes sort of like a zigzag pattern. Let's call this distance capital D. Let's call the time needed to cover capital D capital T. So capital D and capital T should be greater than their lowercase counterparts, right? No, actually. Although capital D is greater than D, capital T is equal to T. But how could this be? Well, there's an easy answer for that. Tons and tons of experiments have been made to conclude that the speed of light is always constant. The Michelson-Morley experiment, for example. This means that capital T is equal to lowercase t. In order for a beam of light in a box at rest and in motion to remain the same speed, something has to give away, and that something would be time. So while 10 minutes may have passed for the box at rest, a mere 1 minute may have passed for the box in the UFO. This means that the faster you travel, or the closer you get to the speed of light, the slower you travel through time. So although you may experience time normally, an observer would see you gradually move slower and come to a halt while you accelerate to the speed of light. This would also mean that an observer would see you move backwards in time if you accelerate faster than light. Okay, is your brain hurting yet? Because our next idea is Heisenberg's uncertainty principle. To start off, let's discuss the shortest measurement of time. Is it a minute? A second? No, both those answers are wrong. In the world of quantum mechanics, the theorized shortest period of time is called Planck time. For you mathematicians out there, 1 unit of Planck time is equal to 10 to the negative 43 seconds. That means 10 with 43 zeros behind it, smaller than a second. This number is defined as the arbitrary limit for measurable time. This means that anything that happens within that instant is smaller than Planck time and therefore unmeasurable. Now, let's get back to the uncertainty principle. Ben Gilliland, editor of Astronomy Now, has summed up this concept perfectly. He says, and I quote, "The shorter you look at something, the less certain you can be of what's going on." End quote. So what would happen if something was observed at Planck time? you wouldn't be able to measure anything that is going on. So literally anything could be happening within that time frame. So theoretically speaking, anything is possible within Planck time. Remember that. Okay, now that we have our two core ideas, how do they create matter from empty space? Truth be told, empty space or a vacuum is never really empty. Why? What takes up space in a vacuum? There is actually something called virtual particles that constantly appear and disappear from space. They're not exactly real, since their existence is dependent on Heisenberg's uncertainty principle. So, what are they? How are these virtual particles made? Let's say, for instance, that there is an electron accelerating through space. Let's nickname our electron electron 1. In the middle of electron 1's journey, it accelerates past the speed of light. Now here is where it gets a little bit trickier. Us, right now, as omniscient beings, we know that for certain that electron 1 is still accelerating through space, right? But what if we add an observer watching the scene being played out? Let's call this observer Bob. According to the theory of relativity, if you travel at a speed faster than light, you would be seen moving backwards in time by an observer. So Bob would actually see electron 1 decelerate and move backwards in time to before it passed the speed of light. Let's call Bob's perceived electron electron 2. However, electron 2 is now slower than light. It will now continue being perceived, moving forwards in time. So Bob would see the electron move forwards in time like we do, then backwards, then forwards again. To physicists, a negatively charged electron moving backwards in time is equivalent to a positively charged positron moving forwards in time. So essentially, a positron is created by the reversal of time. But what is a positron? A positron is an antiparticle, which means that it possesses the same properties as an electron, except it's positively charged. Its charge is the opposite. So at this instant, there are three things going on. Electron 2 is moving backwards in time. A positron is moving forwards in time. And our electron, electron 1, continues its journey. At this point, there are two more particles than we have started with. Electron 2 and the positron are considered virtual particles. We'll talk about that a little bit later. And this seems pretty solid, right? However, we do have two problems, since we're breaking some fundamental rules of physics. Number one, nothing can exceed the speed of light. I'm pretty sure you've heard about that before. And number two, you can't create something from nothing. And despite how contradictory this may sound, there is a way around this problem. What if I told you that this entire series of events plays out within Planck time? The uncertainty principle tells us that anything is possible within Planck time, including traveling faster than light and matter appearing from nowhere. This way, we aren't breaking any rules. But how do virtual particles limit their existence within Planck time? If they exist for any longer, they certainly wouldn't be possible and violate the laws of physics, right? Well, luckily enough, an electron is negatively charged and a positron is positively charged. So it would make sense if they cancel out, right? In fact, this mutual annihilation occurs almost at the same time they pop into existence, therefore staying within Planck time. This is why virtual particles are defined to be reliant on the uncertainty principle. As crazy as it may sound, virtual particles are real, as confirmed by Gordon Kane, director of the Michigan Center for Theoretical Physics. So now that you know how virtual particles are created, how have they affected us? as stated by Ben Gilliland, virtual particles make up most of the mass in an atom, end quote. That would mean that we are mostly comprised of virtual particles. So next time your science teacher tells you that we are mostly made of empty space, atoms are mostly empty space, you give them the spiel about virtual particles. Virtual particles are also responsible for the strong nuclear force. This is the same force that holds together protons and neutrons in the nucleus of an atom. Virtual particles are known to play a role in the existence of atomic bombs. Yes, the same atomic bombs that were tested and used in World War II. They were dropped on Hiroshima and Nagasaki, two cities in Japan. These were the events that ultimately led to the surrender of Japan in World War II. Atomic bombs gets its power from nuclear fission, which is caused by the interaction of specific virtual particles, the W and Z bosons, but we won't go off on a tangent about that. That is a topic for another day. So let's go over a brief summary about this lesson. Number 1, the theory of relativity states that the speed of light is constant, and the closer you get to it, the slower you move through time. Number 2, the uncertainty principle tells us that anything is possible within Planck time, the smallest measurable unit of time. And number 3, empty space is filled with virtual particles, matter that pops in and out of existence. So if you are ever feeling a little bit lonely while you travel through space, just remember your little friends called virtual particles. Thanks.